Okay, in this particular problem, we're asked to calculate a particular potential difference, which is going to accelerate charge from rest so that it passes through a velocity selector undeflected. So let's talk about what's going on here. We can imagine that there's a couple of plates here with a small hole in them, and there's an initial little ion at rest. And there's a potential difference between these two plates, which is given as delta V. So if we nudge the ion into these two plates, it'll be accelerated through them and pass through the holes. Now, after it goes through the holes, the ion is going to be flying with velocity V through a region of space. In that region of space, there's a cross electric and magnetic field, so I can draw the E field this way. And the B field will actually be into the page. They're at 90 degrees to one another. And we know from what we've talked about in lecture that this is a velocity selector. So there'll be a force down from the electric field, but a force up, QV cross B, from the B field. And at just the right velocity, these two forces will cancel, and the ion will go through undeflected. So what we need to do is, the first thing we need to do is we need to figure out what this velocity is for this particular problem. So let's calculate the undeflected velocity. Now, there's a very simple expression for it. The undeflected velocity is just the value of the E field divided by the value of the B field for the geometry given here. Okay, so let's look at what we have. We have an E field of 55,000 volts per meter. Now it's an SI unit. I'm going to go ahead and choose that to write that as newtons per coulomb, which is the same thing. That's over a B field of 2.25 Tesla. That's also SI, and a Tesla is a newton second per coulomb meter. Okay, so if I look at this expression, I can actually do the division, find out that the voltage, or the, excuse me, the velocity that'll pass through this velocity selector undeflected is 2.44 times 10 to the 4 meters per second. Once I know that velocity, I can figure out what the accelerating potential has to be. Remember, the charge started at rest. So the final kinetic energy, 1/2 mv squared, is going to be equal to the magnitude of the charge Q times delta V. Remember, the change in potential energy is just the charge Q times the change in electric potential delta V. Okay, well I know that I've got 1/2 times the mass of the charge, which was 5.3 times 10 to the minus 26 coulombs, or excuse me, kilograms, times the velocity squared. We just calculated what velocity we have to have. Okay, said plus E, so the charge here is 1.6 times 10 to the minus 19 coulombs. That's times delta V. Okay, once we have an equation like this, we can just solve for delta V. It's pretty straightforward. We find out that delta V is 98.6 kilogram meter squared per coulomb second squared. Okay, if I just put in the various units. Well, a kilogram meter squared per second squared is actually a joule. So this is 98.6 joules per coulomb, which is another way of writing a volt. So the potential difference that's required in this problem is 98.6 volts.